Physics 2 students, it's time to complete static fluids, so let's get started. Hey, what happens to an object when it's surrounded by a fluid? What will the pressure be like on each side of the object, and what are the implications of this? Because this thing is submerged, this goldfish here is submerged in a fluid, it's going to get pressure on it from all sides. Same with this hot air balloon. It's going to get pressure, external pressure from the atmosphere. Okay, due to the differences in the pressure, because the lower part of the object, whether it be a fish in water, whether it be a hot air balloon in air, it doesn't matter. It's going to receive pressure, and the lower part of the object is deeper in the fluid, so it's going to get an upward pressure that's greater than the downward pressure on top. Pressures on the sides are going to be the same, because that would be weird. It would violate conservation of energy if it gets pushed side to side. So we get a net upward force. This is called the buoyancy force. Here is how you derive that buoyancy force, at least for a square object. If you want to do it for a random shaped object, you're going to need a little calculus. But our buoyancy force ends up being the density of the fluid that you're in, the volume of the fluid that's been displaced. Okay, so that is not always the same as the volume of the object itself. In this case, it is. And in fact, if we go back, oops, right here, the volume of the fish and the volume of the displaced fluid are the same. The volume of the balloon and the volume of the displaced air that should be in this volume, but is displaced by the balloon, are the same. But that is not always the case, which we'll see a little later. So just be careful of that. And G, so rho Vg, and rho and V are for the fluid. That's important. That's where we get messed up sometimes. Okay, so buoyancy force is emphasized rho Vg with a fluid subscript. Now remember that the density of an object is the mass over the volume, or the mass equals density times volume. So if you see here, we have a density times volume. And so this is the mass of the fluid displaced. And so m times g is weight. So buoyancy force is actually the weight of the displaced fluid. How much fluid you can displace, that's how much force it's going to push up on you. And this is Archimedes' principle. And supposedly when Archimedes discovered this, this thought, he was in a bathtub, and he was so excited that he ran through the streets of Syracuse yelling Eureka. So, okay, now, think Newton's third law, because that's still in play here. If the fluid is pushing the object up, the object must be, by default, pushing the fluid down. So, whenever you get into a swimming pool, the pool pushes you up, the fluid in the pool pushes you up, you push the fluid down, which means that you make the force on the bottom of the pool greater than it was before. Okay, objects surrounded by water. What happens to the water level in the beaker when the object is submerged? Okay, so when I take this object and I put it in the fluid, the water level is going to increase. Okay, what are the implications of this? Okay, so remember from our last video that the height of the fluid determines the pressure in the fluid. So when the water level goes up because I've submerged an object in it, then that means that the pressure on the down here has gone up in the fluid. So therefore the pressure on the bottom of the container goes up, which is just what we said. The same thing as Newton's third law, right? That when you get in a pool, the water level is going to rise, and it's going to increase the pressure on the bottom of the pool, which increases the force on the bottom of the pool. So we did this in class in a submerged observation lab. So what we did is we had a spring scale here and a balance here, and we had an object attached to it by a string. And then in position 1, you're right above the fluid. In position 2, you're just submerged. And in position 3, you are being suspended right above the bottom of the container, but not touching it. Okay, and I asked you guys to observe what happens as we descend. And we found that as we go from 1 to 2, from above the fluid to just below the surface of the fluid, that the scale reading here decreases because the buoyancy force goes up as we displace more and more and more fluid. And that displaced fluid gives us a bigger buoyancy force, so there's less need for us to hold up on it, and the scale reading goes down. However, as we displace more fluid, the water level gets higher and higher and higher, which increases the pressure on the bottom, which made this reading go up and up and up. The amount that this reading on the scale went up is equal to the amount that the reading on here goes down. And if we actually touched the bottom and released it so it sat on the bottom, then this reading would be the weight of the beaker and water plus the weight of the block, because the reading on here would be 0, because the balance is now supporting the whole thing. Okay, when will an object float? Well, the easy solution is whenever the buoyancy force is as big as the weight of the object. Okay, buoyancy force equals the weight. But remember, buoyancy force equals rho vg. So if we plug that in, we get rho vg equals mg, but the g's cancel. And this is the mass of the block. And the mass of the block is equal to the density of the block times the volume of the block, right? That's our definition of density. So we plug that in, we get the density of the fluid times the volume of the displaced fluid equals the density of the block times the volume of the block. And if the volumes are canceled because it's completely submerged and they're identical, then we see that an object will float whenever the density of the fluid is equal to the density of the block, or the density of the fluid is greater than the density of the block. The object will float. The general rule of thumb is object floats when they are their density is less than whatever the fluid is. So if we go back to that floating fish and the hot air balloon, they float because they're less dense. For the goldfish, less dense than water. And for the hot air balloon, they're less dense than the air they're in. That's why you don't float, because you're more dense than air. But you do float in water because you're slightly less dense than water. Okay, so we just said an object floats whenever the density of the fluid is equal to or greater than the density of the block. But wait a minute. Wait a minute. Steel is has a greater density than water. Why does a ship float? So here's our hint. Floats, sometimes doesn't float. Okay, if this is the steel that's in a boat, if you shape it like a boat, it will float because it is able to displace enough volume and weight of water to float. If you put a hole in it, then it will only displace as much volume as the object itself and not this extra air gap in here. And it won't float. It'll sink to the bottom if you put a hole in a ship. Okay, speaking of ships. So here is a classic problem. Pirate ship hides out in a small inshore lake. It carries 20 ill-gotten treasure chests in its hold, but low on the horizon, the lookout spies a gunboat. To get away, the pirate captain orders the heavy treasure chest jettisoned. The chests sink to the bottom of the lake. What happens to the water level of the lake? Okay, think about it for a second. It was all floating originally, the chests and the boat. So therefore it had to displace enough volume of water to float. But once you toss them overboard, they no longer displace as much volume because the buoyancy force is not great enough to make them float anymore. So here's the ship beforehand. This is what it would look like if you had the ship alone. But once you throw this overboard, notice it will no longer displace enough volume for it to float. So therefore, the water level, when you throw it overboard, decreases. Because this weight is no longer displacing as much as it was before. When it's in the cup, it forces extra displacement. So here's the ship alone. Here's the ship with this in the water. You take this out, put it in, and now it displaces more. It's a classic trick question. It's actually a really hard question to visualize when you first are going through this. Okay, floating objects. Discuss the buoyancy force on this partially submerged object. What do you observe? Do you see that? Actually, why don't you pause the video and see if you can write down everything you observe and what you know to be true. So look at this through your forces and fluids glasses and see what you see. Write them all down. Okay. Now, did you see that the object was floating? So therefore, the buoyancy force and the weight of the object must be the same. So these two must be the same. And did you also know from fluids that buoyancy force equals rho vg? So therefore, which is the same as the weight of the displaced fluid. And did you also notice that it wasn't completely submerged? That's important. So that the volume of the displaced fluid is not the same as the volume of the object. That's huge. All right, so in order to float, an object needs to displace a weight of fluid that is equal to its own weight. This will always be true if it's floating. And just be careful how you calculate this volume. The volume of the displaced fluid is not the volume of the object. It's, in this case, since this is our little rectangle here, the area of the top and the height, the height that's submerged, or the depth that's submerged if you wish. Okay, that would be the volume of the displaced fluid, which is less than the volume of the object. Keep that in mind. All right, an object is held below the surface of a fluid by a string. Describe everything you can about this situation. Okay, I would like for you to make a list, stop the video, and make your list. Did you write down that the buoyant force is greater than the weight of the block? I have a picture of it here, so it's easy to see. Buoyancy force is greater than the weight of the block because the string is holding it down. Did you write down the density of the block is less than the density of the fluid? It's trying to float, so that means the block is less dense than the fluid. Did you write down that the volume of the block and the volume of the displaced fluid are the same in this case because it's submerged? Did you write down that the tension force here plus gravity force down has to equal the buoyancy force, or that the tension equals the difference between the buoyancy force and the weight of the block? Did you write down that if you cut the string that it would accelerate up, that this would be the net force on the block now, and it would accelerate up just like a normal F equals ma problem? Now, assuming there's not too much viscous friction from the fluid. And our last one, once the block is floating at the surface, the volume of the block and the volume of the displaced fluid will no longer be the same. All right, excellent. Okay, objects that sink. How does the volume of this tank compare to the volume of the displaced fluid? Well, it's completely submerged, so they must be the same. How does the buoyancy force compare to the weight of the tank? Well, it's sunk, so buoyancy force is less than the weight of the tank. Okay, if you draw a free body diagram of this, there will be a normal force up from the surface of the bottom of the ocean. There will be a buoyancy force up. Those two up will equal the weight of the object down. Okay, one last question. A submerged block is held up by a string. Describe everything you can about this situation. So make a list, pause the video, and make your list. All right, did you write down that the buoyancy force is less than the weight of the block because it's trying to sink? Did you write down that the density of the block is more than that of the fluid? The volume of the block and the volume of the displaced fluid are the same because it's completely submerged. The tension in the string up plus the buoyancy force up must equal the gravity force down, or the tension in the string is equal to the weight of the block minus the buoyancy force up. Did you write down that if the string is cut, that the block will accelerate downward, F equals ma? And finally, the block lands on the bottom of the container. When it gets to the bottom of the container, there's no more tension, but it's still in equilibrium. So this normal force upward is now equal to what the tension force was, because it stopped it from moving down any further. That's it. Our next topic is dynamic fluids. I'll give you a video on that pretty soon, and I will see you later. Bye.